So this is the last talk of the workshop. Jarrett unfortunately couldn't make it earlier in the week. So Jarrett, well, Juan Pablo introduced Jarrett, so I don't have to introduce him. And he'll be talking about mixed mode.
You saw the video?
Oh, I did. I was watching. I was there.
Oh, and the talk is also being recorded and live streamed.
Cool.
And he's going to be talking about mixed mode automatic differentiation in Julia.
So before I start, I didn't really know what people's backgrounds would be other than optimization. So who here has like directly used any like AD library? Okay. All right. Okay. Who here has actually like implemented AD of any sort? No. Okay. Forward mode or reverse mode or both? Sorry. Do you know which mode? Forward mode, reverse mode?
Oh, I can't remember. It's quite a long time ago.
Okay. Okay. Cool. Okay. So then I guess I've maybe hit the right sweet spot then. So this is mainly going to be a talk about forward mode and reverse mode in the theoretical sense, and maybe a little bit of Julia code thrown in, and then a lot of kind of my qualitative musings on what the current state of the ecosystem is and what it will be like in the future. So I guess I'll start off with my own little introduction. I have been working on AD for a couple of years and have been writing Julia code, I guess, for a couple more years than that. I was previously, before getting hired by Juan Pablo pretty recently, working in the Julia group at CCL under Alan Edelman, where Julia, the language, was born, I guess. And there, I did work on AD, but I also worked a lot on performance regressions testing. So if you've done some benchmarking in Julia, you've probably used one of my packages, benchmark tools. Also worked on the CI service that we use for base performance regressions testing, which is NanoSoldier, which runs on a server here at MIT. I started to work with Juan Pablo just a couple months ago, and the kind of goal for the summer has been to do a whole second pass at a lot of our native Julia automatic differentiation tools. And my secret or not so secret goal is in the fall to start working directly on Jump and maybe getting to a point where we can start replacing some of Jump's backend AD with these native Julia AD tools and kind of unifying the ecosystem a little bit. So just to temper expectations, I usually consider my users to be smarter than me. I have no formal optimization background, backgrounds in physics. A lot of my work targets other Julia developers rather than end users. I do provide, I guess, end user APIs to my libraries, but it's hit or miss. I listed a couple of the downstream packages that use my work. So Jump does use a little bit of the native Julia language AD. Shout out specifically to Celeste, which is a pretty large-scale variational inference project going on at Lawrence Berkeley. And they're using AD and Julia in general to classify light sources in the night sky as galaxies and stars and eventually other astronomical objects. So I guess let's just start off with forward mode AD. Is anybody here familiar with the concept of a dual number? Okay. Oh, we got Andreas in the back. That's cool. All right. So I usually go a bit slower here, but I think I'm going to go back quicker so we can get to reverse mode. So this is a dual number. It's this guy right here. It's kind of like a complex number, except instead of I squared equaling -1, we set epsilon squared equal to 0. But we say that epsilon isn't 0. So epsilon can be thought of as an infinitesimal algebraic perturbation that we're appending to some real scalar. And so this is kind of the normal way people start off learning AD, because if you do some algebra with this, you realize that passing it through a continuous differentiable function outputs essentially a truncated Taylor series multiplied by whatever coefficient you gave it here. So these are basically perfect for differentiating scalar functions. Scalar functions are easy to differentiate, and people aren't too worried about those. But for higher order, higher order and higher dimensional functions, we would need to get a bit trickier if we want to do something efficient in forward mode. And so what we've done for ForwardDiff is we basically extend the dual numbers to multiple dimensions. So now instead of having a single perturbation that you append to a single scalar, you have a whole basis of orthogonal perturbations that you can append to the input components of a vector, say, and then track partial derivatives that way. So once again, these are just orthogonal infinitesimal perturbations that are appended to the input and just propagate through your computation in the same order of evaluation that you would normally execute some code.
So that's no longer univariate.
Sorry?
That's no longer univariate.
Right. So you have x, which is still a scalar, but then you have a vector of y's, essentially. Multiply those perturbations. And so this makes it a little bit more clear if we have some input vector, and we would like to seed these perturbations on the input vector so that we track partial derivatives with respect to all of the inputs. We essentially zero out the rest of the perturbations, and then just only apply the perturbations orthogonally along the basis dimensions. And then if we evaluate this, we find it gives us something similar to what we had up here, where we have just the primal value of the function applied to the input value and the derivative at that same point. We get basically the same thing, except that instead we get this function evaluation here, and then we get a gradient out. So we have all the partial derivatives with respect to this function at this input. So with code, this looks a little bit like this. We have a partial derivative. So we have our dual number. We have a partial derivatives storage vector here, and we just store scalar for the value. It's subtyped to real for some programmatic quirky reasons. Obviously, dual numbers aren't real numbers, but this is actually, I argue that this is actually the correct thing to do with Julia's type system. We can essentially start defining the algebra dual numbers just by overloading base Julia methods. So obviously, this is really simple. Once time, we just evaluate the function on the value, we evaluate the derivative on the value, and then we propagate this to the partials. So this ends up being, if you strung together a bunch of these computations, if you did sine cosine of dual, it would essentially be evaluating the chain rule at every step. And that's what that multiplication is doing. So I think it's cool to note that this is all the code you need to enable a couple of interesting things. First, derivatives to arbitrary order. These things can be nested. Sine and cosine derivatives of complex number types. So if you want to do some complex differentiation, you can by just putting a dual number as the real field of the complex number. And it also enables derivatives of our custom number types. So this comes up, for example, in interval arithmetic. We have a colleague, David Sanders, who works on the validated numerics package. I encourage everybody to check that out. It's pretty cool. And he has shown some interesting demos taking subgradients using dual numbers inside of intervals. So just as an example of this in actual use, we're going to take a Jacobian. And we're going to be taking a Jacobian of the cumulative product function here. And then there's math definition. It's pretty straightforward. Julia definition. If you didn't believe that AD worked in a sense, maybe this would be a good stress case for you, because it's got conditionals. It's got a similar call over here. It's looping over things. It's destructively indexing into an array. So we have a bunch of programmatic operations going on that isn't just straight math, and the propagation still works, and we'll see it work. So before we actually show it, we just want to make sure that we have the theoretical basis for what we're going to do. So we have our definition of the Jacobian here. We have all the scalar output functions applied to the input, and then the gradients of each of these functions along the rows. And if we think back to seeding our perturbation, or if we have a perturbed input vector, we can expand this as applying to each of these scalar output functions. And then we kind of get, just by substituting the gradient definition we had earlier, we get the gradient out here as well. So So just to pick a smaller dimensional example with some actual values so that we can test it, this is pretty easy to verify by hand. So we should, if we give our thing a vector of 1, 2, 3, we should get out this Jacobian. So here we have our input. Our input vector is 1, 2, 3, and then we're seeding the perturbations. So we have the zeros here because otherwise there would be these non-orthogonal perturbations interacting with each other along the basis dimension that we're tracking, and so we end up getting some other kind of junk result. And we'll see a little bit later that that's actually a bug that arises in AD implementations quite frequently. But so this is essentially the representation of what we constructed here. And then if we just pass this into the cumulative product function we defined before, you see that the thing that pops out is the Jacobian over here. And so there's a little bit of work to do if you're like making an API for this in terms of like doing the seeding for the user and then doing the derivative extraction for the user. It's all pretty straightforward to like see what's going on. So the thing I mentioned before, perturbations erroneously kind of mixing. This is referred to as perturbation confusion, and it's kind of a very tricky bug. And I'll see if I can actually describe it successfully in a way that it makes sense. But it's kind of if you have to. I had to work through it myself before I understood what was going on. But so I had this kind of pseudo code mathy representation of taking a derivative over some function. So I have this function here, which closes over another function which is being differentiated inside of this function. Okay, so that's kind of messy. But if you just work through this, and this D being like a differentiation operator, if you just work through this mathematically, it's not too bad. You find out the answer should be 1. Okay. If you actually do this using the dual number we defined earlier, you're going to get 2. And the reason why is because, well, so let's think about what we're doing here. So if we're starting at this step with our original function, to get this derivative, what we're going to do is we're going to say, okay, replace this y with a dual number, the value 1, and then we're going to seed it with a perturbation. And then we're going to say that the derivative is whatever is equal to the coefficient on this perturbation at the end of the computation for this guy. And so we have this x here. So now we're going to do our second substitution. We're replacing x in this computation with another dual number that has the exact same value as this one, because this is a value 1. And we're going to seed its perturbation as well. And so what you get is this x being closed over causes the perturbation out here to leak into the perturbation in here. So essentially what you really want to do is you want to say, I want to inject this operator is injecting a perturbation that's then collecting a derivative result. And this operator is then injecting a perturbation that's collecting a derivative result. And if we were like seeding appropriately how we were before with having the orthogonal perturbations be orthogonal along the input dimensions, then we would have made these two perturbations orthogonal. But from a programmatic perspective, if we're just doing naive substitutions, then you don't actually end up doing that. You just place the same perturbation. If you're just using the positional index to refer to which perturbation is which, then you're going to place the same perturbation out here that you place in here, and they're going to mix. And when they mix, it's going to accumulate the derivative information incorrectly, and then you're going to get the wrong answer. So this class of bugs is pretty weird and complicated and crops up everywhere in AD implementations. And there's a lot of AD libraries that they just allow it to happen because it's such a nasty case. And then ForwardDiff was very recently one of those libraries until a couple months ago when I finally figured out the right way to fix this, which is basically just to disallow cases where they might mix. And the way you do that is, in an enforceable way is you actually tag the perturbations based on the differential operator that you're applying. So you really do say, this perturbation came from this operator, this perturbation came from this operator, and if the perturbations ever try to mix, then you can just throw an error. I mean, that's not as good as having it go through, but other implementations kind of, you can hit a slow path very quickly if you have the code to check for that kind of logic. So ForwardDiff implements the thing we just saw, but it implements it with a tagging system, which, besides preventing perturbation confusion, also resolves a lot of nested differentiation ambiguity. So if you're defining a function that's like multiply or whatever, and you have a dual on the left and a dual on the right, and the dual on the right happens to be a nested dual, the question you have to ask yourself is, do you want to propagate your, do you want to apply that left-hand dual to the outer dual of the right-hand side, or the inner dual? And so it's very tricky, and you basically have to pick a convention that you then enforce with your method definitions, and it's very difficult to do that if you don't have a tagging system, because it's hard to say from which operator the outer and inner perturbations came from. So it's worth noting that ForwardDiff's dual numbers are like all stack allocated and very aggressively inlined, and that ends up allowing the implementation to play really well with SIMD. And we've seen some speedups like 4x or so, just from that, basically for free, because LLVM's auto-vectorizer pass is able to just turn instructions on dual numbers into SIMD instructions, which is pretty cool. It provides an API instead of exposing dual numbers directly. It's pretty simple. There's some higher. If you're a power user of ForwardDiff, you can make sure that everything is non-allocating, and you can allocate the work buffers for it and pass them in. Kind of the usual stuff. And the way this is used by Jump is for calculating Hessian vector products. So it turns out, so Jump has its own way of calculating gradients using reverse mode. And if you have a gradient function and you seed just with a single perturbation one of the inputs, then you can get and you run the function, then your output then is essentially a Hessian vector product. And which Hessian vector product you take basically depends on how you seeded the perturbations. And so it's like a really neat trick that people in optimization I think tend to use quite a bit. Okay, so now let's move on and talk about reverse mode. So before we get into the nitty-gritty, it's worth comparing it to the things we just talked about. So instead of propagating an input perturbation forwards, what we're going to be doing is we're going to go all the way to the output and then propagate a sensitivity backwards. And so this can be thought of as just evaluating the chain rule in the opposite order of forward mode. So obviously, if we need to do this and get all the way to the output, then we need to have some type of reversible computation graph. And this seems to be the main hurdle in implementing reverse mode in general, is figuring out in what format you want this graph and how you're going to get it from the user, and what your traversal semantics will be. So the two main paradigms I would say are, you can essentially have the user declare a graph, and that's more what Jump and TensorFlow do. Or you can, if you're doing nested, if you're doing native automatic differentiation, so on a language that wasn't built explicitly for AD, then what you're probably going to end up doing is dynamically intercepting function calls by implementing new special objects that will record what happens to them. And so that's what ReverseDiff does, which is my other package, and that's also what AutoGrad and PyTorch do, if people are familiar with those machine learning tools. So there's a question that I get pretty often, which is which mode is right for me, and there's a split in the regime where it's very clear that you should use reverse mode, or very clear that you should use forward mode, and there's this big swath in the middle where it's not clear at all. So generally, if your output dimension is lower than your input dimension, you should use reverse mode. But this is predicated on the fact that you're going to be recording a whole graph, so if your program is like extremely large relative to your input dimension, then it might not be worth it, because you might have to store an incredibly huge program just to have a theoretical, computational benefit. Forward mode is essentially the reverse. If your output dimension is greater than your input dimension, since we only have to, so the reason why this is the case is because we're kind of counting how many seeds we have to apply, and for every seed. So for the multi-dimensional dual numbers, we were able to add a trick where we could do multiple. We could propagate multiple seeds at once. Reverse mode, it's a little bit harder, but generally, the number of passes you have to perform over the function, or the target function of the computation graph or whatever, is linear in the number of seeds you have to manage. So with forward mode, you apply maybe like one seed, and that can, if you have like a scalar to a vector function, you can apply one seed to the scalar, and you'll get all the derivatives out with respect to that input in the output just by executing that function once. With reverse mode, you would have to, since we're applying these seeds on the output rather than the input, because we're calculating sensitivities on the output and then propagating it backwards, you would have to do the same number of backwards passes as there are output dimensions. So this is kind of the performance complexity game. You start playing, it ends up being output dimension versus input dimension, and then code size versus the number of variables you're using. And so maybe this will become a little bit more clear once we actually start getting into an example. So I've failed at, I think, lecturing about reverse mode a couple times now, and so I've changed my slides, and so I'm hoping maybe this is a little bit better, but I'm still not sure that I'm great at it. So we'll see whether this works. So what I have on the left is the code representation of some function, and we don't know what it is yet. This is basically our knowledge that we're discovering, and on the right we have the graphical representation of this function. And so if we were doing what ReverseDiff does, we would essentially be passing our objects in, and they'd be x1 and x2, and then we would be recording the operations that happen to them, and then we will have information by the time that first forward pass is done. So essentially, the first operation that gets recorded is sine, and then we get a cosine that gets recorded, and then the outputs of both of those operations get recorded, and then our function's over. Okay, so now we have the full function represented over here in code and represented over here on a graph. So what we're going to try to do now is we're going to take some values, we're going to run this whole thing forward, and then we're going to look at the output, and then we're going to calculate the gradient with respect to the values that we did. But before we do that, I want to do something that will just make it a little bit visually easier, I think, to represent the computation. So I have this graph. I'm going to topologically sort it. So I'm going to take this graph and generate a tape of instructions from it, where parent nodes come essentially before child nodes in the tape. So basically, you sort it in such a way that the dependencies are all in the proper order. And an easy way to do that is to just start at the last node and then do a breadth first traversal up. So we can write our last instruction here, and then our next to last instruction, and then our first instruction will be here. And so this is generally the process that that a lot of I think PyTorch uses this pretty extensively for like larger graphs, where, for example, calculating the output sensitivity only requires a certain subtree of the total DAG. And so you might want to generate a topologically sorted list of instructions that only represent the instructions you need to calculate to actually calculate the sensitivity of that function, rather than running the whole computation graph, because there might be things that don't link into that specific output. Okay, so before we start, just to make sure we're clear, we're going to be using the multivariable chain rule. So it's essentially the chain rule, and it just tells you what happens if you have two independent subtrees of dependencies that you are propagating up backwards. So if I have some function that is, I don't know, so I have sine of x equals y, and then y might then go to another function here, and it might go to a different function here, and then those would run and have their own subtrees. And when we were propagating back up, the question is, okay, if we were just propagating one back up, we would just multiply because it's just the chain rule. but we have two different branches off of y here. So how do we essentially combine these? The chain rules tell us how to do that. Well, I mean, it does. It's a linear relationship. You just add the two results. And so that's why this is saying, okay, you propagate that intermediary derivative of all of each parent, and then you add them all together. We're going to refer to our partial derivatives with respect to inputs, partial derivative of the total output, which George calls x5. We're going to refer to these as our adjoint variables, and we're going to denote them with y. And if we do this, we can easily just write down which adjoint variables we want to calculate if we're going to get the gradient of this function. We want y1 and y2 because we want the derivative with respect to x1, derivative of the output with respect to x1 and x2. Okay. So down here, we're going to have our value storage and our adjoint storage, and then over here we have the tape that we generated earlier. And this is a pretty good representation of what you actually have to store, I think, on a computer. You have to store basically these variable values, and you have to store the tape itself. So just propagating it forward, we're going to set x1 to 1 and x2 to 1. We calculate sine, and then this hooks into x3 here, and sets that to the appropriate value. Do the same for cosine, and then now we have our output. So now we have our live variable storage over here has all of the forward pass values in it. And now we're going to start with the reverse pass. In the reverse pass, we set y5 equals to 1, because remember, y5 is just the partial derivative of x5 with respect to x5, and so that's going to be 1 because the change is literally, yeah, makes sense. Just following our chain rule, we can calculate x3 to be x5 times the partial derivative here with respect to x4, or with respect to x3, which is x4, and then do the same for y4. So we say, at every instruction, we're essentially saying calculate the y's for the inputs of the instruction. So x3 and x4 are the inputs of this instruction, x5 is the output. So we calculate y3 and y4, and then we add them. Okay, we get to our next instruction. X2 is our input. So y2 is what we're going to be calculating. We do the exact same thing. X4 is our output, so we use y4 as our accumulated sensitivity. We propagate it with the intermediary partial derivative. That's just this transform. And then we see that, I mean, this is y2, so we already have one of our partial derivatives for our gradient. And then going back up, we do the same thing. We get the other partial derivative. So what we did one forward pass with a bunch of values. We did one backwards pass with a bunch of values. We had one seed. So this is essentially seeding the output sensitivity. And then we got two partial derivatives out of it. So remember, with forward mode, for us to get two partial derivatives in one pass of the function, we would have had to have two seeds. We would have had to have two orthogonal perturbations. So that's kind of illustrates the computational complexity difference a little bit. ReverseDiff is a package which implements this on native Julia code. It uses operator overloading, which Julia is quite good at. And it for example, if you have like a static graph, it can do that forwards and backwards pass that we talked about, and it can do it over and over and over. If your graph is changing with each iteration, for example, if you have some complex control flow that's based on whatever values are being propagated through it, you can re-record the graph, and then that way the operations that you record will be true to whatever the function was, or whatever the function call was. One thing that's unique to Julia is because we have runtime type information, and because of JIT compilation, we can generate specialized compiled primitives for all the nodes in the tape without having to do any crazy like switch case or something, because we can just use dispatch. And this is kind of cool because then if we have something like an array operation, then it can dispatch not only on the fact that I want to intercept it with my own array type in ReverseDiff, but it can also dispatch on the fact that maybe the underlying array type is a symmetric matrix or a Hermitian matrix or whatever linear algebraic matrix is in the base linear algebra matrix type zoo. So it's cool that it falls back to operations that are already specialized for the structure of the arrays that are already being used. Or same thing kind of applies to number types, but usually doesn't matter as much with number types, right? So as I guess I already alluded to, it's ReverseDiff supports array primitives and linear algebraic derivative definitions, and so that's more in line with what you would expect from like a TensorFlow-ish or PyTorch-ish system. And a lot of traditional optimization AD packages don't care about array operations, and they just write everything as scalar operations. And another cool thing is that ReverseDiff can actually leverage actual mixed mode AD, which I guess was in the title of my talk, but I haven't really talked about that much. And so what this can do is essentially say if you have an intermediary scalar subgraph in your expression, you might say to yourself, this subgraph would be more efficiently differentiated using something like ForwardDiff than it would using something like ReverseDiff. Maybe it has only 2 input variables, but it's a very large subgraph. So for that, we give users the ability to pretty easily just mark functions as like forward differentiate this and don't reverse differentiate it. And it uses ForwardDiff to actually perform that. And this includes scalar kernels for higher order functions for element-wise methods. So if you do something like a broadcast sign or something, since there's no cross-element dependency in that, since it is like guaranteed to be an element-wise operation if you're using broadcast or map, then it's actually more efficient to compute that using forward mode as well. And this whole declaring a scalar subgraph as a forward mode primitive, then essentially gives the user, it requires a bit of work on our end, but the user gets those kinds of element-wise optimizations for free. Yeah. So all of that stuff is stuff that I've been working on over the past year or so, on and off. And in that time, I've had a few realizations about where I think things are and where I think things want to or should go. And so I guess, first of all, the first observation is that Julia is really, really good at this, surprisingly so. This paradigm of multiple dispatch and JIT compilation really allows you to just take any black box piece of code and inject whatever you want into it, as long as it's what I'd call, I guess, numerically typed generic. There's some more specific definitions in the package documentation as to what I mean by that. And it's performant. Users don't have to rewrite their code. It's pretty nice given the performance that you get out of it. So the other thing is having everything in Julia actually allows, for forward mode, I already mentioned it, nested differentiation works just by nesting dual numbers, and that's cool. But it's even cooler to me that if you have a Julia represented DAG and your Julia data flow semantics are defined in Julia, then you can actually do these nested data flow operations on these stacks. So you can if I have this whole reverse mode process, I can actually take a computation graph and do the forwards reverse mode pass over it, and I can treat those passes themselves as a new computation graph, which I can then do forward reverse mode passes over it. And this, I think, would be a bit harder if I wasn't working in a single language. If I had to lower to C++, there would be some bottoming out where a primitive would be a primitive, and if things were not constructed using just those primitives, then it wouldn't work. With this Julia code, I can essentially write my forwards and backwards semantics how I would normally write them in Julia, and then they can just be differentiated themselves, as long as they're actually differentiable. So, yeah, just tying into this, it's really nice that adding new primitives is just done via adding normal Julia methods. So there's no magic. You don't have to go into C++ to implement a new array operation or something. You don't have to know some like weird graph semantics. You just add a new method. I will say that it's not. There is some boilerplate code in ReverseDiff right now that is required to actually do this, and it's not so pretty. And that's not really the inherent fault of the method. More so, it's just the fault of me being lazy about making that an exposable API. And I intend to fix that, which we'll get into later. But and then the final thing that's pretty cool is because there's this notion of having different Julia array types that are just backed by different hardware devices, and I can support whatever array types I want. We basically get heterogeneous device support for free. So Simon Danish is a colleague working in Berlin on GPU arrays, which is basically provides what it sounds like it provides. And if you do want to define hardware specialized primitives, you can just overload whatever method you want on, for example, the GPU array type. And I think that's really cool because it alleviates a lot of pressure on me to support GPUs and doing all that work since Simon's doing it for me. So the other question I started to have, and especially after talking with Miles a bunch, is it would be really cool if we could eventually replace ReverseDiff sparse with ReverseDiff, because there are a couple of advantages. ReverseDiff sparse doesn't support array primitives. It doesn't directly support native Julia code. It's not numerically type generic, which I bet Miles might even have an argument about. Would you agree with that statement?
No, I just didn't care.
Okay. And it can easily handle nested differentiation. So there are a bunch of reasons why we would want it, but there are some blocking issues right now, which is essentially that ReverseDiff sparse is really fast for the cases that Jump cares about. So large-scale Hessian calculation, ReverseDiff sparse, as the name would imply, it exploits sparsity in the Hessian to really reduce the number of computations you need to do for the forward and reverse passes. And it also has better variable storage locality for scalar operations. So part of supporting array operations for ReverseDiff involved passing around a lot of pointers, and so I kind of kept that same method for the scalar ops, and that ends up making it a bit slower if you have a very large scalar expression graph than ReverseDiff sparse would be. Because ReverseDiff sparse just passes around indices to an external buffer of variable storage, but it's also hard to do this and still stay type generic as well. There's a whole, it's a whole mess. But eventually I think these things can get resolved in ReverseDiff, and then it will be a suitable, viable replacement. So the thing is, as I was working on this, I wasn't really focusing on the machine learning community at all, because I work so often with Miles, and so I guess ReverseDiff ends up getting tailored to the random things that Miles requests. Lucky him. So, but I did have a bunch of people start using it for deep learning, or attempting to, and then I realized, this whole other regime existed. So what machine learning people tend to like, it seems, after I've reviewed some of these other libraries, they really like APIs, which exposes the variable construction and tracking mechanisms directly. And I mean that's internally what ReverseDiff uses, but the API we expose doesn't expose that functionality at all to users, very purposefully, because my thought would be that they would screw it up. But it's also the case that they tend to like having dynamically re-recorded computation graphs, and this seems to be the case because their regime is one in which they have far fewer nodes than traditional optimization problems, but the nodes themselves are way fatter. They're array operations, and the traversal overhead and the record overhead is very small compared to actually executing the graph. So ReverseDiff does have this dynamic recording pass, but it is implemented as if it's only ever going to be run once, and then you're just going to run a static computation graph thereon after. The whole idea of supporting complex control flow was not too much of an issue for me, because I was like, okay, if you really care about performance, you're going to have a static computation, you're going to run it. In the machine learning world, that's not true, and so they kind of focus on making sure that their record and traversal overhead is, it doesn't have to be low, but it has to be just low enough to not inhibit progress, since they're going to be rerunning it every iteration. The recording mechanism that ReverseDiff uses is really greedy, and so we'll do a lot of allocations during that record process in kind of preparation for the static traversal, which is very nice for the static traversal, but can be a little bit complicated and not so nice if you're going to dynamically record every single time. So we covered that. So it would also be cool to just use ReverseDiff as a native Julia to DAG library in general. I haven't seen a library out there that does this sufficiently. Most DAG frameworks in Julia now have a pretty explicit kind of formulation, a la TensorFlow, or the other one I think is just called Data.jl. They rely on special syntax. You can't take like a black box Julia function and turn it into a computation graph. And I think if you could do that, it would actually expose a lot of really interesting and cool techniques, including the ones I list here. So dynamic code analysis, operation scheduling. ReverseDiff already does a lot of pre-allocation and memory management, so that if you have some like allocating function, it will often write a computation graph out that does the equivalent operation, but it will pre-allocate memory and then translate allocating functions to non-allocating functions. Interval constraint programming, I was talking about earlier, my colleague David Sanders works on that, and I found out when he was working right beside me that he was re-implementing a lot of the stuff ReverseDiff had already implemented in terms of tape traversal and metadata propagation, and then serialization of Julia code to other DAG frameworks. So you could write a Julia function, pass it to this library, and then run it on TensorFlow. Maybe. I'm not totally sure how valuable that would be, or what it would look like, but theoretically it's a possibility. Could be pretty cool. It would require a lot of refactoring of the taping and execution mechanism, because right now they're tied to just passing forth partial derivatives. But it would also just enable better AD anyway, because there are a couple AD techniques that rely on propagating metadata that's not derivative information. So the really important one that I'm going to be working on later this summer is this edge pushing algorithm for sparse Hessian calculation. And so that requires propagating a separate dependency tree along with the values, so that you can establish where like linear and nonlinear dependencies fall in the graph. So all of those kind of concerns and opportunities got me thinking, like, maybe I should just write a Julia to DAG library, and so that's now what I'm doing. I call it Cassette because there's a lot of opportunities to shoehorn in audio puns, and that's always a good thing. So so it's a Julia to DAG data flow package for forward and back propagation of values in arbitrary metadata. I try to kind of appease both the traditional optimization and deep learning communities with the way I've structured this. So I have different representations for static and dynamic graphs, and you can go between them pretty easily. And I've done a bit of thinking to try to figure out what the performance regimes of both are. And it exposes these mechanisms as an actual like useful API to downstream library authors that they can then use to hijack the processing that the package does. So you can say if there's going to be a primitive that I want to record, you can overload a method using normal Julia code that overloads the record operation for that primitive, or the play operation for that primitive, or the rewind operation for that primitive, et cetera, et cetera. There are a couple of these modes. It makes cassette primitives pretty easy to define and extend. And the reason why I know this is because I've started refactoring ReverseDiff to use cassette, and it is a bit faster already. And I have all of scalar differentiation in ReverseDiff right now is maybe like 100 lines of code. So as far as I'm concerned, I've succeeded, at least in part, on making it overloadable in the right ways. But I think time will have to tell whether or not this generalization kind of actually extends to things outside of AD. I'd like to especially start working on interval constraint programming stuff with David Sanders, because I think that could be also useful in the optimization world as well. So that's all I have time for. I'd like to thank the people on this slide. So obviously Juan Pablo, who is now paying me, which is great. And then Cosmin Petra, who is paying Juan Pablo to pay me, which is also great. And so this guy is a scientist at Lawrence Livermore, and he is really interested in an edge pushing algorithm in native Julia. And they already have a prototype of it, but I mean it's not so ReverseDiff and ForwardDiff are more robust and more widely used than the package they implemented. So we're trying to kind of share the knowledge. So I'd like to thank the Julia group. One of those members is here, right there, Andreas, because I still sit in that office and I still bug him all the time about random things. Robin Ditz, I didn't really mention what he contributed in this talk, but he came up with a pretty cool method for optimizing the static computation graphs and getting rid of dynamic dispatch by pre-computing a dispatch table for the tape. And so if you care about that, we can talk about it later, but I just wanted to give him a shout out. And then obviously the meetup organizers. I really do appreciate the chance, I guess, that Miles has given all of us to hang out with each other. And I'm looking forward to, I guess, talking with you guys later. Yeah, so that's it for me. So, questions or lunch?
I would just make one comment. I'm not sure. I would be very cautious about diving too deep into like the current deep net algorithms, because based on what I've seen, they seem very preliminary. I think there's going to be a lot of progress made in how do you do that. And right now it's very brute forcey. So.
Right. I've actually talked with some people about this well, I talked to Intel people who were raving about how NVIDIA's marketing is what's winning the day, not their technology, because they're able to convince people that you can do a lot of very short jumps is better than doing a couple of clever long jumps because you do it on the GPU, right? I'm not too concerned. Yeah, so I am a bit cautious about diving too deep. I think more my interests at this point lie in realizing that there's another type of graph traversal performance regime that I haven't optimized for, and the question is like, okay, well, can I cover all these phases?
But that regime might be gone in like 2 years.
So I don't think that. I mean, it might be used for a different purpose, but it's specifically the idea of having smaller graphs that are dynamically recorded and are mainly composed of array operations is useful, perhaps, for things besides deep learning, right? It's useful for scheduling, as I was talking about earlier, dynamic code analysis and scheduling parallel operations. It's something that I think is a regime that goes beyond deep learning. It just wasn't a regime that I had encountered before talking to a bunch of deep learning people who were complaining to me about it.
Me neither.
Yep.
Well, first of all, I do not deserve to be on that slide.
I saw you debating with Miles about how to encode the timestamps or whatever. You were there.
I was there.
I called all theory. So I guess you made Joey too.
Yep. I should have added you. I'm sorry, Joey. Your name's only one letter off from Cody, though. That doesn't really help, does it?
But I do have a question. So, what could possibly be done for like non-smooth things? Can you get like a sub-differential set or something?
Yep. So there are multiple things I think that people do. One is to take your computation graph and try to rewrite it into a form where you won't encounter any jumps where you're not actually trying to take a derivative. And that's called abnormal form. And yeah, I don't really know much about it. The other idea is to try to automatically decide, oh, I need to calculate a subgradient here instead of calculating a derivative because the derivative isn't well defined, but the subgradient is. it's right now we don't do any of that stuff automatically. I think so. Our definition would just cause some contention, but is also kind of okay for practical purposes for like the absolute value in ForwardDiff is just to look at the sign bit, and if it's positive, then it has a positive derivative. If it's negative, then take the derivative from the other side, which is not that's not rigorous at all, but it kind of works for practical purposes because in floating point operations, for example, like when are you actually at 0? Like obviously there is a 0, but deciding where the discontinuity is for practical purposes would be deciding some threshold on rounding that you would have to care about. It's a complicated question, but people do think about it. That's also why I'm really interested in the whole interval constraint programming world and the whole interval arithmetic world, because if I can use those things to efficiently calculate subgradients, it might enable some methods for those sorts of problems.
Is there at least theoretical work on this?
Yeah.
Okay.
The AD community is really big into abs normal form, and the AD conference me and Miles went to last year also had a talk by a guy who was just talking about intervals. So there, I think they do care about it quite a bit. There's a bit of literature on the subject if you Google for it.
So in theory, Cassette could actually can propagate whatever you want. So it could potentially propagate the subdifferential set.
Yep, that's the idea.
So you could pick the one and say you get the whole subdifferential set, and then you pick not just one subgradient, you pick some set of linear independent subgradients that might be more stable.
That'd be cool, because IPOpt is only there really for smooth stuff. But if we could write optimization algorithms that use subdifferentials.
Yeah, no, definitely. So I'm wondering if you could lie to IPOpt and just like give it a subdifferential. That's like let it do its thing and see what happens.
Would it be a heavy lift to use, say, Cassette and to compute a symbolic derivative graph?
No, you can propagate expressions as your metadata.
Yeah.
And that might end up being, so currently there's a package called Calculus, and it is like, so John Miles White, who originally authored, is a really great guy, but I think he's
one of the first Julia packages.
Yeah. It was originally like super cool, but at this point it's been like years and it's acquired a bunch of corrupt and nobody's really rewritten it. And so right now I think both our symbolic differentiation story and our finite differentiation story is like pretty bad, just because that package is so old and it's only maintained like just enough to keep it running. And so I think eventually I would like to make a symbolic differentiation package that was a bit better, and I kind of had the thought recently, and it's like, maybe I can build something like Cassette. But anything else?